All right, my guinea pigs, let's resume where we left off before. So you remember we analyzed this little decryption routine, right? And that was decrypting this part of the code base. Now it is decrypted. We noticed also those guys, right? Remember those offsets on top of A6? And you remember also that they were matching offsets in the exec library from the Amiga OS, right? So for example, -78 was disabling the hierarchies. Okay? So let's start after the decryptions, right? So here you have the same thing, right? They identify, like they get like some a long word relative to A6, so the base of exec base basically, with an offset, but this time it's positive, right? So let's see what it is. So if you look at the headers, right, for the Amiga OS, and you go to the execbase.h, basically where they define this, where this A6 this A6 register is pointing to, right? It points to this, right? And in there you have a lot of like various data, right? So you have the library itself, but you have like a bunch of various things. The thing is, like, when you reverse engineer the code, it's a pretty long list of members, right? So I started to actually compute the offsets manually, but I just gave up. So and I basically made myself a program to actually print what are those offsets. So let's go through this. So this is an Amiga C program. I just include the exec base here, right? And I basically go through all the fields one by one. I just copy pasted them and just like change the line to match those, right? And I define myself a little macro here that gets the offset here of the symbol, and compute what's basically in bytes, what's the distance between the beginning of this exec base and the specific field, right? And I go through all the fields. So I compile that with an Amiga compiler, VBCC. Pretty cool. It works. You can cross-compile, so I compile comfortably on my Linux machine, and I put that on an emulator, and the output is like this. So suddenly I have the same table as what we have for functions, right? But this time for fields in this big struct. So let's see. For example, so the first one is 3A, okay? If I go to my little reference now, 3A, oh, this is this. So this is system stack lower. So system stack lower. So system stack lower is this is basically the base of the stack, the bottom of the stack in the system, right? So I guess that the virus wants a place to put some things, right? Like and at the beginning you don't have much things. If you can use the stack, of course, it has the stack initialized, but I guess he wants to copy something somewhere. We'll see later. I don't know yet. Then we see that it zero out D0. Okay, cool. Then so the quad works, so the entire register. Then it moves DF00. So this one is HPOS. It's basically where the scanline for the video is, right? I was mentioning that just in my previous video. That's usually used to to get a random number, because like the synchronization between video and wherever you are in the code is basically a little bit random. So you'll get like something that is kind of pseudo-random. Then it multiplies by 12 this thing. Then, oh, that's curious. So BCLR is basically setting a bit at 0. It puts the bit number 0 at 0 for D0. This person needs to get some math lessons, right? If you multiply a number by like an even number, right? Like just you did, and then you reset the first bit. You basically transforming an even number to an even number all the time. So this is useless. This is just like I think that's just a reflex from a developer to say like, yeah, I want to have an even address, right? So because it's a 16-bit processor, right? You don't want unaligned numbers. Then, oh, look at what it does there. It adds this basically this random offset plus the C stack lower, basically. Okay, so basically that's a point somewhere in the randomly in the stack where it's not used yet. Okay, so now you see that they get 226. If I look at 226, that's the kick tag pointer. They simply check if this pointer has been initialized or not. Then it goes to check the cool capture from the structure, and something just checks that is it initialized or not. And finally, the last one is they are testing for cold capture. So those three pointers, right, are three different ways to make something resilient to reset. So kick tag pointer is like an extension mechanism for the kickstart, right? You can basically add some resident module. You can add a resident program, right, to the that they will execute at the beginning, right? That's a way to because the kickstart is in ROM, right? So you need a way to, if you want to install, like, I don't know, new programs that starts at the beginning, that's a way to do it. Cool capture and cold capture are the same thing, but lower level. The kickstart pointer is kind of like higher level, but those two ones are very early in the boot. For example, if you want to initialize a peripheral, right, you install a driver, and if you don't want the kickstart to reload it every time, if the user resets, right, it can actually, right at the beginning, before anything starts, actually access and initialize the hardware. And cold capture is a little bit later, right? Like that's basically in between those kickstart and cool. So that's a way basically to insert a resident program, right? And depending on where if that has been initialized, it goes to EE. So here. Or it goes to CE, so basically here, right? Okay, now if you look at the first branch, this one, you see that, so it moves the, okay, A1, that was where we were roughly in the system stack, right, to D1. It swaps D0, so basically the 16 bits, higher 16 bits will become the lower ones and vice versa. D1, same thing, and then it compares the words. So it basically compares this roughly A1 and D0, so the thing that was already recorded in one of those vectors are roughly in the stack somewhere, right? That it should not be, right? Like when you think about it, those vectors should not land somewhere in the system stack, right? If it is, it kind of recognizes that, oh, that's already mine, right? It goes to EE, and it looks like that's where we go there. And on the other side, what does it do? So it loads the current position compared to the program counter, that is like 1558 in that reference shows of addresses. So 1558, that's probably the beginning, right? Yeah, that's completely the beginning in the right on the top, right? And what is it? So 1558, right? That's the top of this code base. Now, if I do, it adds A0 to A1. So A1 should point to the random spot we have on the stack, right? But what I suspect is that it will copy itself on the stack here. Look at that. Here it has the counter of like that's the full size, right, of the boot sector, and there you recognize this pattern now, right? That's a copy. Because you have like a A0, which is where it is at the beginning, like where it points to, and A1, this is the spot on the system stack, right? And then until it's not that until it's not 0, right? It continues to copy. Okay, that's the loop. So that means that this one is basically the beginning of the sector, which is this one, like in that referential, plus AA. Where does it puts us? 0x1558 plus 0xAA. Okay, that's 1602. Boom, here. So, now it means that PEA is loading on the stack, the current stack, right? An address that is pointing basically to where this pointing to where this here will be, right? After the copy, so it will copy that somewhere, right? And then push this address on the stack, and then after the copy, look, it goes into an RTS. RTS will what it will do is it will unpile or depile the address from the stack and jump to it, right? So it's a kind of like it emulates a function call, and a return will basically jumps into that spot, but at the new space where it copied itself. All right. So the first thing it will do, it will jump to a subroutine, right? So let's put that clearer. So we have that. So it will be there, it will jump there. That's the first thing it will do. So it will load, so A6 is still the base of exec, right? So it will load 226, we know this one, that's the current kick tag pointer, right? So right there, basically it tests if it was touch. And if not, basically it save the jump address 1910 to A0, right? So what is this 1910? Oh, that's basically in the middle of the buffer somewhere in there. Then it saves 8 bytes later into A1, okay. Then saves the address of it into this A0 spot. Then saves 4 bytes after. Sorry, a little bit later. It saves also the original kickstart pointer, right? We saved at the beginning, right? So basically, it gets like a private jump back to the original routine, right? And then saves A0, so its original address in the kickstart, right? Pointer. Then what does it do? A little bit later from A1, it saves kind of a constant. Oh, I see what they're doing. This is probably a jump, right? Where 1.8 DE, is it still in 1.8 DE? This is somewhere CDE. Oh no, that's the string Lamer Exterminator. It saves that as also a spot in the array. Then saves 169A, so this one. 169A, yeah. Okay, so I think it's not documented -264, but I understand what it is doing because it returns in D0, and D0, this is the kick checksum. So basically the kickstart checks if this original exec base is actually still good, right? And it does a checksum of itself. And that saves whatever they modified here to inject itself into the kickstart pointer. Kick type pointer, sorry, it modified the checksum, right? So it needs to be coherent again. So this -264 probably is like a private function that computes, recomputes basically the checksum for this data structure. Then we start to see here the same pattern, right? Here it basically save one of those function call pointers that is undocumented neither, right? I don't know what they are intercepting. That actually doesn't really even matter at that point. Then here change it to 16AA, which is itself, right, in there after all those trickery. Then let's see. So this one minus C6. This is alloc mem. So basically it allocates a little bit of memory, and then here it saves basically in 1908, which is again the private space you have below, right? It saves the allocated address. Then it takes the address of 15E from the structure. So let's see what it is. So 15E. Oh, this is the device list. right, it loads 18cc. So 18cc, which is track disk device. Then calls an exec function 114. We should be able to spot that quickly. 114 find name. So it finds basically the device in the list. Device. So D0 is probably the answer. Then it saves one of the function. So A0 is basically the beginning of the structure with it's the same. It's going to repeat that exactly as the exec base, right? So negative pointers are functions, right? So it gets one of the functions, might be read, or actually at that point we could guess, right? Then save the original one somewhere in its private space, right? 1904 through this. Then save its own function at D4. So D4, that's going to be this, which is like then at the entry point from a redirected track device. So imagine a read or a write, right, on the floppy disk, and basically insert here like insert itself, right? So here I was wondering where this 1908, this allocated memory basically is used, and you see that it is used in the middle of the redirected entry point for the track device. So probably that's where it manipulates buffers, right? When you are reading from the disk, right? It needs an intermediate buffer to inject itself. Okay, so then here that is enabled. So that's the end of it, right? Like it redirected whatever it needed in both the kick tag portion, right, and the track device. And now it looks like we'll check, but it looks like it continues the normal boot as if would have done here, like in 1699A, which is where it registered itself on the kick tag, right? So either it jumps from there when you do reset, or it jumps from there when it loaded itself and installed itself as a resident, right? So then what does it do? It loads an address that is stored on 190C. Did we see what is 190C yet? Yeah, nope, we haven't looked at it yet. So it tests that if it is 0, right? You just have like some logic there to call 78. So 78 is, I believe, disable. Okay, we disable here the IRQs. Or here it subtract 1 to the content of this address. So maybe there is a counter somewhere for the behavior. Let me see. So that is disable, sorry. It calls 1652. 1652. Which is basically be sure that be sure we actually redirected the track device. Okay, okay, I understand now. So this is just to check if we already if we are from above, right? We already redirected the track device, or if we are coming from the kick tag, right? Where probably the structure has been reset from the original one, so it wants to actually redirect the track disk, so it can reinfect the next disk we insert, right? So this is the one, right? Like this is basically All right, then it points A0 to another like 1910, another like private space. Then saves in D0 2 to 6. Let's see what it is. Oh, it's again the kick-tack pointer. So why is it doing this? Then goes to 166, 160 here, otherwise. Oh, it does again the same thing, really, for the kick tag here. I don't really understand why, but yeah, basically here again it does the same thing to insert itself on the kick tag. So I believe that when, okay, I understand now. So the kickstart probably resets also the kick tag, right? Like it does for the track disk, right? So it reinserts itself for the next time around when it will get reset, right? So that's this part. Now after that it returns. So we are at the end of the boot sector, basically. That's the entry point when it goes to the track disk device. Sorry. So here it's probably not very. It's probably a bit less interesting. Like it's just about re-emulating what was done in there and basically putting itself in the buffer and write to the track 0 to infect it. So all right, we know now that it redirects the track disk device and inserts itself there. Now probably there is a part where it just copies itself. That is not really interesting, but I want to find something else in there. And I think I spotted something. So let's look at this constant, right? Let's compute that. So let's look at 4C, see something there. It's strange to me. What if we do, how do we do this? Like this, I think. 72, 21. Bam! Ha! I recognize ASCII. That's why I did that a little bit like intuitively. So you see that here it copies somewhere, probably in the buffer, right? Like this string we saw, right, in the previous episode, Lamer. And look, we have a DBRE, right? That loops over this, and a counter that is 54. So what is 54? 84 times. So basically, that's a nasty behavior you cannot observe, right? So we found it. That's 84 times. So now when does it do this, right? Let's see a little bit earlier, right? 184C. So here it just jumps over. So it compares something that is relative to A0. So yeah, it basically compares 8 to something that is 3 bytes. Okay, so that's a little bit random because when you see what is saved at 1908, that's basically the allocated address that the Kickstart gave to the program. So basically, if the last bytes of the address is 8, it will trigger this bad behavior, which is strange. That's a weird criteria to to trigger randomly. So here we go. You have a little bit like an overview of how viruses was inserting themselves into the boot sequence of the Amiga, and a little bit of yeah, what like a kind of a sketchy quick overview about the bad behavior, right, in assembly, right. It gives you also a little bit of sense of how we reverse engineer some unknown source code like that. I hope you enjoy this video, and please subscribe if you want to see more. Also, feel free to share your ideas, right, in the comments below, and see you next time.